Okay, we are recording our session. Welcome to week 5 of Data640. I'm at a conference this week, so I'm a little more helter-skelter than even usual, a little bit further behind than even usual, but I'll catch up. Also been going in and out, seems like air conditioned heat, so it always keeps my summer cold alive and well, but neither here nor there. So this is the week where you finally have to turn something in at the end of this week, which will be midnight Monday of next week, June 22nd, I guess. You need to turn in your decision tree models that you've developed with some discussion. So a little bit more about that later. As I said, we spent last week talking about decision trees and how they work in general. Wanted to spend a little bit of time on how SAS does decision trees. Now, I was going to try to do a live walkthrough. It turns out the program is running too slow. There must be a lot of people at SAS who are catching up on things and sucking up all the server energy because I couldn't get it to run fast enough to really give me confidence that I can finish this in a reasonable amount of time. So I have some screenshots and I'll do some discussion and you'll be fine. Okay, going to talk a little bit about decision trees and how SAS Enterprise Miner does that. Again, let me remind you that there are so many options that it's not my, I can't cover all of them, even if I knew all of them, nor do I wish to just sit here and keep clicking and talking about those things. So I talk about the general ones, some that I think are more useful, some tips, tricks, techniques. You also have people in the class who probably have more experience with Enterprise Miner and can provide other ideas. But certainly we want to talk about decision trees. Now, under the decision trees, you see 3 listed: automatic, interactive, and gradient boosting. Okay. So earlier, I know I said that we were going to save the gradient boosting for an ensemble week. Okay, I'm sort of reversing that idea. If you want to use the gradient boost this week, I think that would be fine. We did it in the spring. We did do the gradient boost in the first assignment, and so I'm not requiring it, but I'll talk a little bit about it tonight. So I'm going to talk a little bit about these, then do a little walkthrough demo with some screenshots and give you some tips and hints and so forth. Okay. So there are a lot of modeling tools in Enterprise Miner. The big 3, of course, we cover in this course in some detail: decision trees, regression, and neural nets. And of course, each of them has spin-offs where you can use them for a classification model or a continuous numerical model. And then there are some specialty ones. Okay, and this DM neural is a specialty one when we get to neural nets. The gradient boosting is a specialty one, which I would have kept for, ensembles and stuff, but they put in here. And then there's some others we're probably not going to get to. And then multiple models, that's where they have ensembles. And the gradient boost really is kind of an ensemble model, so I would have put it there, but they have their own reason for doing things. Okay, so you can create automatic trees. All you do is, well, at the appropriate time, after you brought in set up your problem, brought in your data set, partitioned it, of course, then you can just drag a decision tree node down and say go, and it'll create the tree automatically. Again, there are some things you can modify, and I'll talk a little bit about those later, but that's how easy it is. Bring it down, click, boom, go. The second way you can do it, of course, is to control the splits yourself. User-defined splits, user-defined more options, when it stops, and so forth, how you want to prune the tree. You could do that in automatic too, but basically the interactive lets you decide the splits. Now, why would you want to do that? You might think, well, the automatic tree has got to be better than me trying to outguess the algorithms in terms of where the splits should occur. I mean, we have the Gini index, we have these other measures. Why would I want to try to outguess that? I don't think it's as much a question of trying to outguess it as it is a couple of things. First, you might want to ask, remember the ultimate tree gets turned into a set of rules. If this and that and that and that are true, then the other. Then you're going to probably be a 1 or a 0, whatever the answer is. So it might be that you want to control the flow of the questions. So you'd like to have the split first on something that makes sense for your business. If you're in the tele, cell phone business, maybe the first question you'd like to ask people is how long you've been with us. That might not be the first question that comes up with the automated system. And you might get a better answer, and you might certainly get something more usable, which is more relevant. But it's really good to try the interactive and see if you can outdo the automatic. That's your challenge for the week. Then the third one, of course, is the gradient boosting, which I've thrown back into the mix. Don't again, if you already feel like, gee, I've already done my assignment, I'm not going to do gradient boosting. Well, that's fine. But most of you, I've talked to several of you who did want to try it. So I've said, well, let me throw it back in. It's an ensemble model, but basically it creates multiple decision tree models by resampling the data set and building multiple trees. And then the final one is sort of a weighted average of the multiple models. Now, as with most ensemble methods, the reason you build multiple models is to sort of mitigate the impact of strange and weird occurrences, things like that. And what the gradient boost does is continue to try to tweak the way in which it weights and splits so that it gets better and better and better. Doesn't always turn out that way. Doesn't always turn out that the gradient boost is a better model. When I did a little walkthrough here, my gradient boost did not turn out to be the best one. I don't think there's any reason to assume that will always be the better of the three. So again, I would say try them all. Certainly you need to build several models. We've talked about the fact that with the drudgery or the tediousness of doing the calculations long gone, the key now is to build multiple models, keep track of what you're doing with the settings so that you can sort of put that together at the end and say, now here's the model that came out the best. Let me see if I can gain any insights as to why. Now, unfortunately, and I've mentioned this before, the insights you gain will not be universal. It won't be like, aha, you always want to do X, Y, Z. Nope. It will turn out to be more contextual. Like for this kind of a data set, it might be the best thing to do. But it won't turn out that you have these inviolate rules on how to do the settings, because that would make life too easy. Just like it doesn't turn out that any one technique always outperforms the other techniques. When we get to regression and neural nets, a lot of people think, oh, they must do better than decision trees because they're more sophisticated in some ways or mathematically involved. But no, not necessarily. And certainly they're harder to explain, but we'll come to that later. Okay, so here's my walkthrough problem, having set the stage a little bit. And I'll have a few diversions in this. I'm using the PVA 97NK data set. It's very similar to the donor data set. It's 10,000 cases roughly, a little less than 10,000 cases. It's got 50% of the people did not donate, 50% of the people did donate. So someone has stratified the data set so that we have a roughly equal, well, exactly equal, turns out, number. Now, if you were to just pluck one of those cases out and try to predict whether they would donate or not, you would have a 50-50 chance of being correct because half of them did and half of them didn't. So what we're trying to do, and this is important, right at the front end of your analysis, you want to try to set the objective. What is the objective? It's not to get something that says, I'm 100% sure this guy or gal is going to donate, because that would be very impossible. I mean, that's an absolute answer. What you are trying to do is improve the odds and get the odds to, as it says here, identify those who are likely enough to donate to justify the expense of the mail-out requesting the donation. So you don't have to get 100%. You may, who knows, you get to 55% where you can predict with 55% actually who's going to donate. That might be enough. And that's why you'd want to have in the business world, and it's unfortunate that most of the data sets we use in this course don't have a business context in terms of costs and or profits. I'm looking for ways to change that. I'd like to come up with some problems. Either Sarma has a little bit of help there, come up with some more problems where you have costs and payoffs, because I think part of what the data scientist has to do is get away from strict measures of accuracy, like, you know, the ROC curves and the classification matrix and so forth, and deal more with, okay, what's it going to cost me? As you know, some of you, of course, in the medical world know that, you know, a false positive and a false negative have much different implications than just being wrong. It might cost someone their life, or they might cost someone having to undergo extensive tests that they didn't need to undergo. So there are trade-offs there. And in the business world, there are trade-offs. If you don't mail to anybody, you don't make any money. If you mail to everybody, you probably lose money because it's expensive in this particular instance. So we need to look for ways to do that. If you can find a data set that has a business context, that would be great, but most of them are just business sets. Okay, so the objective is to improve the 50-50 odds, keeping in mind the profit payoffs. Now again, this is some information about it. 9,686 cases, 28 variables. Variables are divided into 4 groups. Demographic variables are demographic characteristics. Gift variables summarize the donation history. So you're probably familiar with this because it's very similar to the donor database. Promotion variables, frequency of previous solicitation, and status variables, recency and frequency measures. And then things are stratified by time, so there's multiple indicators for each of these categories. Okay, and then finally we end up with some characterizations, which is also one of the indicators: first-time donor, new donor, active donor, lapsing donor, inactive donor, star donor. Okay. All this is background, but the reason I put it in with a couple of screenshots is I wanted to remind you that one of the things you need to do in your assignment is, first of all, be certain to sort of describe a little bit what you've got with your data set. What is it? What's it look like? What kind of variables? You don't have to be, remember, you can put an appendix in with a lot of the extraneous material, but it's good to know what kind of data set you're dealing with. Okay, so there are 2 target variables, just like there are in the donor data set. Target B is a variable that indicates yes or no, they did or did not donate. Target D, an interval variable, that's the amount. So this is very similar. In fact, it's just a slight redo of the donor data set that is at SAS. Now, one of the things you do, of course, when you first open up your data set is you can look at the data, the metadata, if you will. And in this case, there were a couple things. And again, this is sort of a heads up. When you first open your data set, you want to look and see if there are any variables that are rejected for some reason. Okay. In this case, the DEM cluster was rejected. Now, why was that rejected? Well, it turns out, if you go to the next page, go to the next slide, there are some default settings. Okay, class levels count threshold. If a variable has more than 20, then it's considered an interval, not a variable, not a category. And down here, reject levels count threshold 20. If there's more than 20, can be rejected. So one of the things I had to do was first I changed the class levels count threshold to 2 so that only binary variables get counted as categories, and then I changed the threshold to 100 so nothing got rejected. And that fixed that problem. So you might want to take a look at your metadata and decide, do you have something identified as a target? Do you have variables that are rejected or appear to be out of sorts, out of order, not correct? And then you can take a look at some of the things you might be able to do with that. Next thing, of course, you want to do is partition the data. We always partition the data. Now, we've had some discussions, myself and some of the students, and there's been some of this in the discussion area, and that's great. I like the discussion. And the discussion has centered about whether or not you really need 3 subsets of your data. We know we need a training set, always, always, always. And we know we need at least one other set to test it on. Some people who have, in some cases, a better SAS background than I do, have made a good case for having 3 sets all the time based on some of the things that are in the help screens and so forth. I have this quote right here that's also right from the SAS documentation. It says, use the data partition tool to partition your data, blah, blah, blah. Write each output data set, train, validate, and test. Now, the next part is where there's a little confusion. Test partition is only used for calculating statistics after the modeling and selection are complete. I bolded this last part because, again, I'm not saying you shouldn't have 3 data sets. I'm just saying I'm still a little less than totally clear as to whether we do or don't need 3 sets. Many analysts regard this as wasteful of data. In other words, splitting it into 3. Now, why is it wasteful? It's wasteful because obviously you're reducing the number of cases available to each of the sets. If you have to divide it into thirds or 3 pieces, not thirds, but 3 percentages, you're not going to have as many in each chunk. Whereas if you can put 75% in training and 25% in one other data set, a little bit better. Therefore, it is not uncommon to omit the test partition and assign an equal number of cases to the training and the validation partition. So there's some, uncertainty. Now you say, well, what do I do about that? Well, you might want to try it both ways. Again, the key now with this enormous processing power, and you're getting tired of hearing it probably, is the ability to create multiple models, try multiple options, and then compare those on the appropriate criterion or criteria. Okay, so after I split it 50-50, the way I did it, you can see from the printout, remember SAS gives you that printout after you run this, it says there's 4,843 cases in the training set and 4,843 cases, instances, lines in the validation set. So I only created 2. Okay, a little sidebar here. You can see this is slide number 6 on the walkthrough. Now we're doing a sidebar. I'm going to do the interactive tree because that's the one that's more fun. Now, obviously, the automatic, we're done. Not much to show there. So it's interactive. You can sort of control the number of splits, the minimum number of cases you want to have in a leaf at the end. You can view the progress and say, gee, I like the way this is going, whereas you lose some of that with the automatic. So when you're just learning to build decision trees, this is probably a good idea. Now, if you always pick the #1 Genie recommended splitting criterion, you're probably going to end up with something almost the same as the automatic. So, all right. So what you'd want to do is go down here and click on this ellipsis and change it to interactive. Click the ellipsis under interactive and activate it. That changes it from being an automatic tree into being a user-controlled tree, okay, an interactive tree. Okay, so when you do that, what will come up is just the single node with all your cases in it. You can see it's very evenly divided. Only rounding error somewhere in there occurred to change it. 4,043 at each. So there must have been a few cases with missing values or something that got lopped off. So if you right-click this node and then select Split Node, you will get the Genie index, actually the log-worth. We'll say a little bit about log-worth in a minute. You'd have to switch to get the Genie index. You get the log-worth. And you can see the higher the log-worth number, and they don't want to call it that anymore. They want to call it minus log P. I'd rather call it log-worth, but that's apparently somebody changed the name. But the higher the number, the better candidate it is for a split. Okay? So that makes it easy. Now, this is kind of a strange creation, this log-worth or minus log P, but it makes sense if you think about it. Here's the background on it a little bit. You've got some of this in your book from Sarma, pages 178 and 179. It's, again, just like the Genie index, a measure of how different the child nodes are from the parent in terms of creating homogeneity. So the larger or the bigger the log-worth stat, the better the candidate for a split. So how do you get this log-worth character? Well, again, the software is going to do it for you, but just so you have a little bit of background, you calculate the chi-square statistic first. And then you test the hypothesis that the split made no difference. And okay, here's the example. Now, some of this is in Sarma, worked out for you, and some of it isn't, but I've got my own example too. Suppose we had all these records, and of course they're either ones or zeros, and then we line them up by income, and so we're trying to decide, should we split on 10,000, less than 10,000, greater than 10,000. That's a candidate split. Remember, the software checks every possible input variable for every possible split value. So it's doing a lot of these calculations. We can do them quite easily for one, but if you had to do it for hundreds or thousands, it ain't going to happen. So this is the thing, again, right out of Sarma, table 4.3. You basically create a little table. You say, well, if I did this split, how many would I get under 10,000 that are non-responders for the total number of the less than 10,000 cases? How many of the greater than 10,000 people would I get who are responders? How many of the greater than 10,000 would I get who weren't? And this is the number of greater than 10,000 cases, and then these are just the totals. So we set up a hypothesis that the proportions of the responders and non-responders are the same for people making less than 10 grand versus more than 10 grand. That's how we. This is again another chart right out of Sarma, but let me give you some numbers to go with it. Okay, so let's say I made these up. We're considering splitting on 10,000, and we run it through the cases. We find out, of course, there's not 10,000 here, it's just 1,000. We get 50 people who make less than 10 grand who did respond, 125 people who make more than 10 grand and respond, 350, total of 400 people make less than 10 grand in this data set. Small data. Didn't. A total of 600 people make more than 10 grand, 125 did, 475 did not. And then there's your totals. Okay, so this is if we did the split. Now, what is the overall proportion of people who responded? Well, that's 175 over 1,000, or 17.5% actually sent money. 82.5% did not, right? So let's assume we have a hypothesis that there's no difference between these characters as to how they respond. We would expect that of the 400 people who make less than 10,000, we would expect 17.5% of them would respond. If there's no difference between this pot of people and this pot of people, then we should get 17.5% of this pot responding, 17.5% of this pot responding. Well, what did we get? So 17.5% of this pot would be 70. 17.5% of this pot would be 105. Likewise, we should get 82.5% of this pot not responding and 82.5% of this pot not responding, if there's no difference between the two pots in terms of their, in other words, if this variable has nothing to do with whether they respond or not. Okay, so we do those calculations. Now, the chi-square test says take what you got minus what you expected. Okay, I got 50. I expected 70 based on the overall statistics. Square that and divide it by the number you expected. Do it for all the cells. So 50 minus 70 divided squared, that quantity squared divided by 70, plus 125 minus 105, quantity squared divided by 105, et cetera, et cetera. Ends up with a chi-square of 11.54. When you put that into a p-value of chi-square, you get 0.00068. Now, up until now, we don't have this log worth thing, do we? We just have chi-square, which lots of things, lots of tables and software does chi-square. You know, a lot of almost everything does chi-square. So why didn't they just leave it at that with the p-values and all? Well, it'd be a little easier to compare if you could convert those p-values into something else. I mean, here I got a p-value of 0.00068 in terms of significance. I could have another split. I'm going to come up with all these p-values, which in many cases will be rather small. In some cases, they'll be large. Very difficult to sort of think about which of those is actually the best one. So then what they do is take the minus log p, minus log 10, base 10 of that, to get the log worth. And so here's that 3.167. So the log worth for this potential split is 3.167. Remember, the bigger it is, the better the potential for split. Here's the Sarma example on page 234. Same deal, you know. This is what was expected. He reversed the order of the tables. This is what we got. You calculate the observed minus the expected, squared over the expected, boom, boom, boom. You get a p-value, or you get a chi-square of 7.1, which is a p-value of 0.00766, a log worth, which is the log 10 minus log 10. And there you are. So that's different. So a couple of examples, just in case you're wondering what's going on behind the scenes. All right. I think that's really nice. I mean, you could see, well, I could do those calculations. Well, sure you could, but can you do them for hundreds to thousands of variables with hundreds of thousands of breakpoints that are possible? No, not very quickly. So the software says, boom, done, got them all, right? And what you see in the that table, you back it up. What you see in this table is the overall best log worth for each of these variables. Okay, so now we're back to walkthrough. We've decided, hey, I think I like this splitting on this GIF CN36. Okay, So here we go. Okay, so we again select, right click and say we want a specific split. It says we're going to use which one we're going to use. We pick the one we want to use. And then you can split it into 2 points. Now you could split it into more, but I'll say a little bit more about that later. And it says, okay, here's the best place to split it. 2.5. Less than 2.5, greater than or equal to 2.5. Then you just say apply, and it splits it. Now, remember when we started, we had a 50-50 split, zeros and ones. Now that we've split on the gift count 36 months, you will notice it's no longer 50-50, is it? We have a more than 50% zeros over here. Again, this is the training set. Of course, it immediately does the validation set too. And over here, we have a more than 50% ones. So right away, this one split has increased the odds of finding the ones if you're looking for the ones, or increased the odds of finding the zeros if you're looking for the zeros. So that's the whole purpose. So we got some separation. Is that good enough? Probably not, so we want to keep going. Again, if you're doing this by hand, you could say, let me split on this node next. Again, right-click, take the next thing if you want to take. In this case, medium home value region. It splits on 67,350. And again, we went from 57% zeros in this pot to now we got 63+% zeros in this pot. So if your gift count is gift count 36 months is less than 2.5, and your medium home value is less than 67,350, 63+% of you characters aren't going to give us any money. And of course, over here we still have more zeros than ones, but it's splitting these into finer and more homogeneous things. And if we do the right side, same thing. You know, we're going to end up with a higher preponderance of ones, 64% here. So the darker blue is telling us we're getting better and better and better on this thing. Okay, so there's the entire tree after we've split twice. Now, it brings up a couple of obvious questions. When do you stop? How far do you go? Well, go as far as you want to go, but we'll talk about some problems that can occur. One thing you can do, if it's splitting on some kind of an odd value, like in this case, 67,350, you know, again, thinking ahead that I'm going to turn this into a set of rules that I'm going to operationalize, give it to some guy on the front line there and say, follow these rules, ask the people these questions, or check their data that they turn in and see what's what. I might not want 67,350 to show up because that implies sort of an odd number. You mean $1 more, 351, would make a difference? People get bothered by that. But if you want to change the split for whatever, any reason, you can edit it. Okay, you can right click and edit, put in the values you want. So I changed it to 70,000. Now, if you look at the results, you'll see it doesn't do quite as well because I said, well, I'm going to use something different than what you recommend. I'm going to use something with not quite as good a splitting criteria. But, you know, you may want to do that. You may want to split on a certain age or a certain salary or a certain number of months or something rather than what comes out. You can do that. And I encourage you to try a couple and see if it makes any difference. So when you're changing the split, again, click Edit Rule, put in the values you wish. When you click Add Branch, it will add a $70,000 branch, and then you go and have to eliminate the 67,350. Right click and delete it. It's really odd the way that works, but that's how it works. You add a branch, so you have 3 branches, delete the one that you don't want, and it'll switch the other one, and then it'll be split into 70,000. Okay, then finally what you could do is just right click and say train, and it will finish the tree. Or you can finish it yourself one at a time. You can see we eventually end up with a tree that looks something like this. Now I know that's illegible, but you've probably done something similar when you did the walkthrough anyway. So you know what the tree looks like. Okay. And the darker the blue, the more we are. Now, what's really key after this point, this is the maximum tree. This is all the way down to where it won't split anymore. Why did it stop at 6? Well, 6 levels is the default for stopping. So it would have gone further had I changed the default to 10, 12, 100, whatever. It would have kept going. Ultimately, it will stop when it reaches whatever that stopping level is, or there are a couple other things you can set as stopping criteria. We'll come to those in a minute. But, splitting it too far down usually leads to overfitting. Okay, we're going to fit exactly to one particular case. I mean, the ultimate would be that there was only one case in each of these leaves at the bottom. It's a very specific set of 300 questions. If you meet that, we know that's not going to do well on new data. That would do well on the training data. So once you have what we call the maximal tree, however you got there, whether it was the number of levels or the minimum number of cases in the leaf or some kind of a chi-square number where if it's not significant, you stop. That's okay. But however you got there, the next thing you would want to do is say, is that the best tree? Remember, best for training doesn't always equal best for validation. And of course, the validation is much more important. So what you do is right-click and get the subtree. Click on View Subtree Assessment Plots. See where the best stopping point is. So here's our training set. You notice that the more splits it does, the better it does on misclassification. That's the criterion we're using here. It keeps getting better and better and better, but notice the validation set gets better and better and better up to about 5 or 6 splits, and then all of a sudden, not so much in terms of number of leaves, not splits. Okay, so we would say, oh my goodness, I need to stop sooner. Okay, and then again, when you plot that, you get the same kind of thing. Here it is on average squared error. Same kind of thing shows up. Right about 5 is the best thing. You notice again, training set continues to get better and better. Validation set, not so much, gets worse. Here it is on the misclassification rate. You can try out different things, and sometimes you get different answers. So, it might be that what's important to you. Misclassification more important or overall error? Of course, average squared error will be used more for continuous models. Here's, again, something right out of the help screen. I'm not going to read that to you, but it talks about the criteria you can use. They like this one called decision. Now, of course, that only works when you have a profit and loss numbers that you can put into your data set. Average squared error, misclassification, lift. I like misclassification for categorical or classification problems. And of course, average squared error for continuous problems. The default is decision. Interesting. So that means average profit and smallest loss if profit or loss matrix is defined. If it's not defined, the value of the measure will be reset in the training process depending on it. If the target is interval, we use average squared error. If the target is categorical, the measure is set to misclassification. Okay, that's important to know. All right. So, again, since we have a classification problem, we're trying classifying zeros or ones, we're going to use the misclassification criterion. There are some alternates, again, that I just mentioned. So we use that, and we tell it, go figure it out, and it says, aha, 5 leaves. Now, if you read Sarma, and you should, because Sarma's great, a little technical on occasion, but really good. That's a good book. He does a nice job of trying to explain the many, many, many things there are in there. There are many. But basically, if you look at Sarma, you will note that he walks you through the way in which the optimal tree is arrived at, the pruning process. The whole reason we pruned it was to get back to this point. Okay? So how do you get back to that point? Well, while it was building the tree, it was checking on these things. And of course, what it really is doing is it can go back and, as it says in Sarma, create trees, take off a branch. You say, how's that tree do? You take off another branch. How's that tree do? How's that tree do? Keep taking off branches, meaning splits, until it gets back to something that performs the best on the validation set. And then that is the optimal tree. So the decision tree that's optimal will be the one that performs best on the validation set. Okay? And it turns out to be this one, 5 leaves. Now, gradient boosting, okay? Again, if you want to try this, go ahead. This is right out of the help screen. There's a gradient boosting node. And again, I would say give it a shot. It's not hard to use. What it's going to do is create a bunch of trees. Almost all the settings I use are the defaults in the gradient boosting. I haven't tried too many expanded ones. So if you want to use the gradient boosting, I would say take a look at some of these things. The help screens are pretty expansive, if not helpful. They're at least expansive, explaining a lot of things. I've done the gradient boosting several times, and I usually use the defaults. They work pretty well. So how'd it come out? Well, you know, here's the max tree, the optimal tree, and the boosted tree ROC curves. Okay, again, against the default, of course, the baseline. So you can see that against the training set, the gradient boosting did do better, the green line, slightly. Against the validation set, it's almost a blur. You know, it's hard to tell who really did better than the next guy on the ROC curve. So what you might want to do is switch the results chart and look at it differently. Okay, you can look at it on these various ways here. Or you can go and get the fit statistics. Okay, now if you put that node on the end that compares all the models, here are the three models: optimal tree, maximal tree, gradient boost. Again, the tendency is to think that the gradient boost is always going to be the winner, but it turns out here it was the optimal tree, interestingly. I'm not sure how that happened, because I would have thought, oh, the optimal tree, sure. I am sure how that happened. I was going to say the maximal tree should not ever outperform the optimal tree, because it could be the same one. If the maximal tree is the best tree, that's what's going to come out the optimal. So you can see slightly better with the optimal tree. What's interesting is that the maximal tree, this is what I wanted to say, is better than the gradient boosted tree. That's not something I would have expected. So if you get something like that, you might want to stop and think, what happened here? Maybe you needed to run the gradient boost with some different options. Maybe it wasn't good enough with the defaults. Okay? I'm going to have to go try some more of those, because I didn't have time this week being at the conference to really mess with the gradient boost once I decided to throw it back in the hopper as a possibility. Okay? But certainly you'd want to build at least one automatic tree. You want to build one interactive tree. That's a minimum of two. You know, as I've asked for in the assignment, at least 3 trees so you can compare them. So you can go build a tree with the automatic and change some of the settings. You can build an interactive and change some of the settings. You can try partitioning the data different ways. So let's talk about a few of the things you could do. Here, first of all, are some enterprise minor general notes. You always build the model on the training data. I don't know how many times I need to repeat that, but I like to repeat it. It just makes me feel good. And you assess it on the testing data, which could be the validation set. You change the settings, parameters, or inputs. One of the things, remember, that the decision tree does, that we're one of the main reasons we start with it, is automatically figures out the inputs. That won't be true necessarily with regression and or neural network models. You have to give it a little more help figuring out the best set of inputs. If you build a decision tree and some of the inputs aren't used at all, which is quite likely, you might go back and see how bad or how different it is. If you force some of that in, you'd have to do that with the interactive mode, clearly. But, you know, what if it didn't ask a question you thought it should ask? Does it make a difference? And if so, is it the difference, of course, should be worse, not better. But it might be a question that somebody once asked anyway. I don't know. Rebuild the model after you change some things. Build your second model and assess the new model on the testing data. Change the settings and repeat the process. So it's an iterative thing. Now that we've got the heavy lifting out of the way of having to do the calculations, we can do a lot more trees. We understand what we're doing a little bit better. We know what's going on behind the scenes, but we are in charge as the person driving the complex machinery, and then we're in charge of making the ultimate decision as to which model is best. Maybe some insights as to why. Again, still on general notes, some metadata notes. I think I've repeated these before. When we get downstream, again, these metadata notes become a little more important with other kinds of models. Include only variables you intend to use in the modeling process in the raw data source. That's not a big deal if you're using data sets the size we're using, but you get up into hundreds or thousands of input variables, and millions of cases, then you probably would like to pare that down. So that if you don't bring them in, you know they're not going to ever show up in the model. Why bring them in the first place and just clutter up the database? For variables that are not inputs, use variable names that start with the intended role. Okay. For a variable that is, well, ID or something, if it's an ID variable. For a target variable, always has to start with target. We all know that already. Inputs are to have a nominal measurement level, should have a character data type, and inputs that are interval must be numeric. Okay, some general notes. A couple more general notes, and I think I've mentioned these too. The default is to bring in a sample, not the whole data set, of 2,000 cases. And it brings in the first 2,000. So if they're ordered somehow, it'll bring in the top 2,000. I don't know why that's the default. I would think the better settings are these. Random, meaning don't just bring in the top, skip around, and bring in all you can. I mean, we have enough processing power now that this is not a problem. The max is 30,000 rows or 30,000 cases, however you choose to view that. So I would think these settings are better than the defaults myself. But you need to change those just one time under Options Preferences, and it'll stay that way as long as you don't change it back. Some specific decision tree notes that might be of use. Okay. Splits and worth calculations. Last week we talked about Gini. This week I showed you a little bit more on the chi-square converted into log worth. Here's sort of the layout as to how those fall. If it's nominal target, yes, no, you can use these three. If it's ordinal, you want to use entropy or Gini. And if it's interval, you want to use variance or probability that measures variance. Here are some measures that you can decide if your validation is doing what you want to do. Decision, which I mentioned was the default. Average squared error, misclassification, and lift. If the profit matrix is used, that gets incorporated, and of course then you'd want to use decision. I like that. I just can't find problems laid out well enough to use. Special case, binary target, use log worth. Okay. Sarma seems to think log worth is the best thing to use for the binary target. Yes, no, 0, 1. Okay. P-value adjustments. I think I mentioned Bonferroni, but if not, think about this. As you go down and do more and more splits, some of the possible variables you could split on will have more possible options to split on than others. If it's gender, you can split on male and female. If it's a number, you might be able to split on 2, 4, 6, 8, 10, 12, 14, 16, right? So some features will have more possible split option levels, which leads to a higher possibility of a false positive decision on the chi-square test. Okay? So you can turn on this adjustment in SAS, which I would do. So after the best split is chosen for a feature, the log worth is adjusted by this Bonferroni adjustment. Okay? It subtracts the log to the base 10 of m, where m is the number of splits. So it subtracts something. What does that do? It makes the log worth lower, doesn't it? Makes it not as valuable. Okay, so that helps mitigate against some of the inaccuracies that will occur if you have something. And this makes a lot of sense. Something that can only split on 2 values versus something that can split on hundreds. You would think you got to do something about that. Depth adjustment. The further you go down the tree, obviously, the smaller number of cases you're getting in each of the leads. Okay, even though you're doing a better job of homogenizing them, getting them all to be the same, there's still a smaller number because you split it in 2 pieces. So when you get further down the tree, you should have a stricter standard for significance. Okay, instead of calculating the p-values the standard way, you take the p-value and divide by the depth multiplier. That's how far down are you? And that results in more splits being rejected than if you don't use it. Again, to me, makes good sense. Sarma makes a good case for that. Guy lays it out pretty well. Controlling the tree growth. Okay, you can set a threshold p-value that says, unless you meet that, you're not stopping. Or you can set the adjustment property, again, threshold. You have to have at least 50 parents before I can split you into 25 and 25 or 30 and 20. and leaf size property. If a split results in a leaf which has less than the value specified, the split will not be made. So these are ways of sort of controlling it. Again, things you might want to try. If you see your tree coming out strange, and if you see leaves ending up with a very small number of cases in them, you might want to adjust some of these things and not split so much. Again, some of that's okay, some of it's not. Okay, so again, split size property, again, set the value. You don't have at least 50 parents. I already said that one. Maximum depth. As I said, the default is 6. Number of splits. You can go, excuse me. What did I do? I lost it here. You can go up to 100. That'd be a heck of a tree, wouldn't it? Pruning, of course, you can grow the maximal tree. Then it eliminates one split at each step, and once they're developed, it picks one of each size. There may be several trees of size 5 leaves, and we pick one of each that's the best one in terms of the accuracy measure you're using. Again, example in Sarma is quite good. Quite good. Miscellaneous. These are some of the defaults for the autonomous tree. Remember, if you just drag a decision tree node down and say run, that's an autonomous tree. You don't do anything. So you may want to look at some of these defaults. Number of splits to create at each partitioning. In other words, it's going to split it into two. One node is going to split into 2 nodes. Could you split one node into 3? And the answer is yes. It turns out, if you read down the bottom, turns out, according to the SAS documentation, there's no value in that. It says any multi-way split can be obtained using a sequence of binary splits. Primary change is cosmetic, so I wouldn't mess with it. Now that's different than having multiple, a multi-target, nominal target that has more values. I'm talking about the splits. So I'm going to split into less than 5,000 to 8,000, 8,000 to 10,000, and 10,000 to 12,000. My next split. No, I'm not going to do that. The metric used to compare different splits, the default is log worth. You can change that. The rules to stop the growing, there's several. Log worth threshold, that's same as a chi-square threshold. Depth adjustment, I only want to go down 5 levels, 4 levels. I'm sorry, this is how many parents you got. Depth adjust, maximum depth, and minimum leaf size, things we already talked about. Pruning the tree model, usually that's done on average profit for a decision. These are the defaults. And the method to treat missing values, best leaf. So it puts the same values in for the one that's the best, having the most values in it. Those are some of the notes I was able to pull out from having done this for a couple of semesters now, getting more comfortable with it. Okay, so I think it's worth trying a lot of those things. You really want to experiment. You want to keep track of what you're doing so you don't get confused. Wonder what I did. That iteration number 7 was great. What the heck did I set? So watch out for the tendency, which some of us did last semester, to click, change some options, then we got an answer. So you can go back and see, but you sometimes forget to check certain things. What did I do? So anyway, okay. So your main activity, and I think most of you are up and running now. Certainly you should be. If you've done that walkthrough with 13.1 and paid attention to the kinds of things we've done in class, you should feel very comfortable about going out and getting it. Now, what you need is a good data set. You may use, as I said, one of the SAS data sets. Look for one that's kind of rich and robust, has lots of features and lots of cases. If you choose to go out and get a real-world data set, there's a couple of kinds. There's the ones at UCI, which I consider quasi-real world. In other words, they're real world, but they've been out there so long and been tortured so much that they're in real good shape. So they're very easy to work with. They're large, but they're easy to work with. Okay, you can use one of those. They're good. They're good data sets. Or you can go get a real world one, and then you might have a lot of work to get the data into the right format, cleanse it. Don't need to do a lot with decision trees. Not a lot of fixing uppers that you need to do, imputing or anything like that. But it might be messier. Okay, it might be messier. So obviously, the larger and more complex data sets you get and do a good job with it, that needs to be rewarded because that's more work, clearly more work. But unless you're extremely comfortable with all these features and things like that, I wouldn't try one of a real world data set yet. You'll have plenty of opportunity to do that later in the course where you'll be more or less encouraged more to do that. Meanwhile, while you're doing all of that, I will be preparing to move us on to the next thing when we talk about regression, both linear regression and logistic regression. One for continuous variables, linear, and one for categorical variables, logistic. Very interesting stuff. And SAS has a lot of interesting ways to handle regression and handles it very well. A lot of it's automated as always, but always gives you the options to change things. So I think it's a fun thing to do. I like all of the models we look at. I love the decision trees. I like the regression. Of course, I'm a huge fan of neural nets. So we'll see. Now, one of the key things to be thinking about as we go along is which one tends to be more accurate, right? So we'll see. All right, last slide. Our time is about up anyway. As always, and I know this may have some of you head swimming because there's so many things, like trying to learn Word and learn all the different fonts and learn all the different ways you can put bells and whistles in there. But the basics are key. The basics are key. Get a data set, cleanse it. If this were not decision trees, you have to do some cleansing. Partition it, impute values, transform variables. Don't do any of that with decision trees. That's why we start with them. And then go and build some models. Make sure you're comparing those models on the relevant measures, and then see if you can glean some insights from doing that. So it's partly to get you some experience with SAS Enterprise Miner, one of the overall goals of the course. The other meta goal or main goal of the course was for you to understand what's going on behind the scenes, because anybody can push the button, but we really need to have some feel for what did I do and why did I do it and what does it mean. And I think that's what we're getting as we gain more experience. Okay, so I'll pause here and say if there are, again, as always, questions right now that you think I could clarify, ask. Questions during the week that all would like to see the answer to. We have this Let Me Have Any Questions discussion area. Questions that are just pertaining to you, certainly email or call me. I've gotten several emails from the class. That's fine, not a problem. I try to answer them as best I can. If it's a question where, you know, again, it would benefit all, it's better to put it in the classroom, because I know we have some people in here who have used SAS Enterprise Miner somewhat more extensively than others. Certainly some of them more extensively than I have, so it's good to get their perspective. I have a lot of time to practice mine, but I don't have I don't have as much experience as someone who may have been using it a longer time. Okay. Well, I'm going to go ahead and stop the recorder. Well, stop sharing. Always stop sharing first. And then I'm going to go and stop the recorder.